Okay, so now let's get started. Thank you all for attending today's webinar. And my name is Yiming Chen, and I'm from Origin Lab Technical Support Team. And in this webinar, I'm going to talk about the two apps called the Statistical Process Control and the Design of Experiments. So first of all, if you have any questions during this webinar, you can just put it on the chat window, and we will help to answer. And also the project and the recording of this webinar will be posted early next week. So you can go to our website to check. So these two tools are introduced in Origin as an app. So if you don't know about apps, I will just quickly show you. So if you go to the lower right-hand side of Origin interface, you can see this Add Apps button, and you just click it to go to the Apps Center, and where you can find the apps that I will cover in this webinar: Statistical Process Control and Design of Experiment. Yeah, basically you will see this download button, and you can click to download and install, and the app will show on the apps panel on the lower left. For some of you, if you don't see, sorry, hold on a second. If you don't see my screen, let me share it again. Hi, Snow, can you see my screen right now? Okay, great. Okay, so I'll repeat. So if you not know about apps in Origin, that you can go to this App Center Add Apps button. You click it, and you will go to the App Center in Origin, where you can download and install the two apps called Statistical Process Control and Design of Experiments. And these two apps I will cover in this webinar. For some of you that you don't see the app, that it's very likely that the content list in this App Center is not getting updated. So usually you will see this download now red button, and you click it, and you will get the latest apps show in the App Center, and you'll be able to download the two apps. Okay. Let's go to the first one, Statistical Process Control. First of all, I will just give a short overview of this tool. So statistical process analysis is a statistical tool that helps to analyze, to monitor, control a certain process, and eventually will to help to optimize the process. And usually the data comes into this tool. Usually it's like a collection of the measurements or observations of a certain product or a certain service that's collected in a point of time. So this is usually like a time series. So the questions that can be answered by this tool is like whether the process is stable, whether the mean, the variation, or fluctuating over time, and some other questions like whether the process will meet the requirement for certain specifications. Okay, and whether the process itself is capable or not. And in Origin, we introduced this app in Origin 2024. Okay, yeah, please update to the latest version in order to install this app. And as I have showed you, once the app is installed, you will see the app icon show in the app panel. To view the tutorial or help documentation of this app, you can simply right-click on the app and say Open App Tutorial web page. Okay, it contains very detailed explanation of this tool, as well as the tutorial and the algorithms, how the values in each tool is calculated. Okay, yeah, if you just scroll all the way down to the bottom, you should be seeing this step-by-step tutorial of the tool and also the algorithm. Okay. Also come with this app, there is a sample data. Yeah, you can right-click on the app and go to the show sample folder. And all the tutorial are based on the data in this sample project, and you can use this sample project to follow the steps in the tutorial to learn this tool. Okay, let's go to the tools one at a time. So if you just click on this app, it brings up this fancy HTML dialog. It comes with a couple of tabs, which is on each tab there's a different tools. So this is a major app that we introduced in the latest version. Okay, so we'll try to go through these tools one at a time. So first of all, I'm going to show the tool called identify data distribution. Okay, so here I have this data, and yeah, if you quickly check the notes of the data, this data is our weight values, which supposed to follow a Weibull distribution. Okay, then we will first use this tool to identify distribution. Let's just start the app. Oh, sorry, I just clicked the wrong one. Start the app and go identify data distribution and click this, choose this tool. So in this dialog, first of all, you just specify the data, and you will specify whether they are subgroup of the data. So in this case, we will just treat each observation or each row as an individual data point. So I'll say subgroup size is 1. Okay, then go to the distribution tab. You can say I want to fit the data to certain number of distributions. Okay, or I just say I want to fit do the distribution fit for all the distributions. Okay, and just particularly for Gaussian mixture model, you will specify a number of components. So basically, this is a mixture of Gaussian functions as a distribution function. Okay, let's say just to specify 3, and there are other tabs. So you can do data transformation. So after a Cox transformation, whether it follows a normal distribution, and there are 2 other data transformation methods. Okay, and you can also check the probability plot. Okay, and the confidence level. Okay, yeah, let's just click OK to see the result. Yes, since I fit the data to all the distributions, so it takes some time for the analysis. Okay, there we go. So in the result table, the stats that we are interested in is the goodness of fit test. Okay, we can simply read the p-value or Anderson-Darling stats to tell whether the fitting is good, and we can simply just read the decision, like the conclusion here. Okay, so basically, if the p-value is above 0.05, we will draw the conclusion that the distribution cannot be rejected. So here we can see a couple of distributions like Cox transformation. So after transformation, it follows a normal distribution, and for it also the data itself follows a gamma and a Weibull and etc. Okay, and if we simply check the probability plot of weight. Yeah, we can check individual plots if the data points on the graph follow the diagonal line, which indicates that the data follow that distribution. Okay, and it also has this the p-value listed here. Okay, so it's like a visual way to tell whether the data follows certain distribution. Okay. And the second tool is the data transformation. So here I have this data. The column B is the number of new house sold for a different area. And if I make this histogram of the data, we can tell it's not normally distributed. and we want to do some transformation. Okay, let me just highlight this column and choose a tool and say data transformation. Again, here, if you wanted to check the help for the tool, you can again click this question mark button. It will also go back to this tutorial page. Let's quickly take a look at the data transformation documentation. So tutorial, yeah, let's check the algorithm. So it lists the Box-Cox transformation expression. Okay, so here I want to use this Box-Cox transformation to deal with the data. So it's like a power-based transformation. It just raises the original data to an exponent. Okay, so here lambda is the parameter. If it's a 1, then it's just didn't make any transformation. If it's like a 0.5, then it's just take a square root of the original data, and etc. Okay, let's go back to the data itself. Okay, so here, because all the values we measured are positive, so here it says, does the data contain values less than 0? I will say no, so I go to the Box-Cox transformation. And then again, like if it's an individual data point, I will say the subgroup size to be 1, okay? And for transformation tab, you can just say, I want to use the optimal lambda value. Yeah, as I said, if the lambda value is 0.05, it's just take the square root of the original data. You can choose to whether to round the lambda to 0.5 or multiple of 0.5. If you uncheck this box, it will just use the optimal lambda value, okay, which might be some arbitrary number. But to make the model simple, we'd better to just round the value. Okay. Okay, let's click OK. Okay, in the report table, we can quickly check the distribution of the data before and after the transformation. Okay, clearly after the transformation, the data is more follow the normal distribution now. Okay, and we can read also the upper and the lower confidence level for the lambda value. Okay, it's since it doesn't cover the value of 1, which means the transformation is appropriate. Yeah, because if lambda equals 1, which means that we don't need to make any transformation. Okay, so this is for data transformation. Okay, now let's go to the control charts. Okay, yeah, control charts helps us to like visually view the process as a function of time. Okay, so here again, I have this data. Yes, let's see. It's the measurement of the height of a certain product. Okay, and first of all, I assume these are just individual data points, the individual measurements. Okay, let's go to the control chart tab. And so here are a couple of options. If you can do a control chart for individual measurements, or if the data, if the measurements are grouped in, then you can do subgroups. And if the data is not continuous, it's like a discrete data, you can do a attributes chart. Okay, let's start with the variable charts for individuals. Okay, here let's try IMR. So again, first of all, I need to specify the data. I can click the button, say I want to measure the height, so it's column A. So I will quickly go through the individual tabs. So do you want to do transformation? So I assume these data follow normal distribution, so I don't want to do transformation. If you have any primary knowledge of the mean and the standard deviation of the data, you don't have to enter here. This tab says like how do you want to calculate the standard deviation of the data? So since the subgroup size is 1 here, I can use the average moving range as a standard deviation. and also you specify a moving range length. Okay. Yeah, there are other settings like do you want to check like a multiple of the standard deviation limit to be shown on the graph? Okay. So there are a couple of criteria to test whether the process is within control. So here, here list of 9 criterion that you can choose from. Yeah, just take one as an example. So 1 point more than k standard deviation from the center line. Yeah, so this is a default testing criterion, but you can click the drop down and choose all tests. Okay. Yeah, we'll talk about the stages later. So other options, yeah, would you like to display all the data on the plot? Let's say yes. Okay, let's click OK. Okay, so it generates 2 graphs. First is the individual values as a function of time, and the second is the moving range as a function of time. And also, some of the data points are beyond the limit. Okay, and you can quickly read the conclusion here, like test 1 point more than 3 standard deviation from the center line. And if you hover your mouse over the data point, you can read the value and the number, the row index. Okay, and also one data point is failed on test 5. Okay, so test 5 means more than 1 standard deviation from the center. 4 out of 5 points more than 1 standard deviation from center line. Okay, and also for the moving average plot, there are also some data points outside the limit. Okay, so which means the process needs to be improved. Sometimes if you want to make some changes to the settings, you can quickly click the green lock and say change parameters. And this will bring you back to the dialog of this tool. And then you can make some changes. So for example, I wanna, for the test, by default, the first point, the NK standard deviation, the K value is default to be 3. If I just make the criterion more strict, so I change that to 2 and click OK, and the result all gets updated and you get, yeah, a different result now. And another thing is sometimes people may want to add a stage to the plot. The stage means during the process of the measuring, people may apply some controls to the process. So there can be improvement of the machine, or maybe change the operator. So people want to have a different control chart at different stage period. Okay, so to apply the stage, I can again click the green lock and go back to the dialog and go to the stage. So I just specify a stage column. Let's say the column B. And okay, I can also just quickly show you that if you go to options, you can show the label for all stages. Okay, if I click OK, yeah, so you will see the control charts are divided into 3 stage levels. Okay, yeah, let me just go back to the if you want to reset everything to the original setting, you can click the triangle button here and say system default. Then every setting will go back to the original. Okay. Another thing is in Origin, if you want to customize the graph, okay, and maybe let me just make some changes to the control chart. Okay, I was just simply do a color filling. Let's say I want to fill to our next plot and make the filling to some customized color. Yeah, you'll see the effect. Yeah, I just make some changes to the graph. You want to make the graph to be prettier, and you want to use this in the future when you make a control chart. You can save this as a template. So you right click on the title bar of the window and save template as, and just leave it, you just use a default name and click OK. Yeah, so next time, if you just make this same type of control chart. Yeah, just quickly show you. Yeah, I'll just make the same control chart, use the default setting. Yeah, you will see it will use the saved graph template to make the control chart. So just so you know that you have this option. Okay. Okay, let's quickly go to the next control chart. So in this data set, instead of just individual measurements, I have these measurements grouped into the time. So for example, the first 4 are measured in the day 1 and the next day 2 and etc. And also for the control chart, the tool accepts more than one input variable. So we can check multiple processes at a time. Okay. So in this case, I have 2 sets of data. Okay. And also these data are grouped into different days. Okay. So in this case, I will say I want to do variable charts for subgroups. Okay. So we have the other options for the different type of data. Let's choose the first one. Okay, so here you need to specify the subgroup. You can specify a constant value for subgroup, or you just use specify a column. Okay, let's say column A is the group column. Yeah, some of the settings are the same, like whether you want to transform the data, whether you have primary knowledge, things like that. And yeah, in this case, since we have a subgroup size more than 1, it has different options to how to calculate the standard deviation. Okay. So if you select R bar, which means the range of the mean range of each subgroup. Okay. Yeah. Again, then you can just choose all the tests. Okay. Let me click OK. Okay. So for data group into subgroups, it will, first of all, the first graph is the sample mean. So it's like mean value of each subgroup is plotted as a function of time. And also the sample range, the range of each subgroup plotted as a time. And we have 2 data sets as input, so it generates 2 sets of results. Okay, and also for each process, there's 1 data point which is out of the range, out of the limit. Okay. Let's go to the next example, the attributes chart. So in this data set, the first column is the total survey, which is spread out to the customers, and the number that gets response. And the second column is the number of users that says unsatisfied in that survey sheet. So in this case, I want to make a control chart for this attribute data. So if I just go to the attribute charts, there are 2 rows of tools. So the first row is for the binomial distributed data, and the second row is the Poisson distributed data. So in this case, the response of data is just a yes and a no. These data fall into the binomial distribution. So we will just look at the first row here. And also another question we need to consider is that if the number of the response here is too small or too large compared to the total responses, that will cause this bias, and we call that over dispersion or under dispersion. So we will need to do a p-chart diagnostic to tell which chart we need to use for this kind of data. Yeah, just quickly show you that we support this p-chart diagnostic. If I click that, and for the input, the measurement data, which should be the number of response that is unsatisfied, so which is column B, and we set the column A as the group size, so which is the total number of responses that gets received. Okay, there are other settings. not very important. If you just click OK, yeah, you may just by reading the graph doesn't give much information, but you can just read the conclusion that the ratio less than the lower confidence limit, which right now the calculated ratio is only 23.4, which is below the lower limit. So it gives a conclusion that using the P chart is not appropriate, but the linear P chart is recommended in this case. Okay, then we will go ahead and use the linear P chart for this data. Okay, so let's go to the tool and just choose the linear P, right? So for the measurement data, let's again column B, and for the subgroup samples, subgroup size, choose column A. Yeah, there's the other settings, and then yeah, I'll just leave the default setting and click OK. Yeah, so we can get a quick conclusion that the process is within the control. Okay, so for this particular chart, you will see the lower and the upper limit is not a straight line because that depends on the subgroup size for each point. Okay. Yeah, this is the control chart for the attribute data. We also support time-weighted charts. Okay. Just to quickly show you, this is the same data we see a moment ago. It's the measurement for two machines, but they are also grouped. So if it's under the time-weighted charts category, yeah, we support the moving average and the weighted moving average and the cumulative sum chart. Okay. So I'll just show you the result for the cumulative sum chart. It just plot out the accumulated deviation from the target. Okay. This is the cumulative deviation for machine 1 and machine 2. Sometimes you want to compare this chart with the control chart for the mean value. So in this case, that chart is in another folder. Okay, so I want to change to the other folder, but in that case, the graph will disappear, right? So in Origin, you have this feature called a ping active window. Okay, so if you click that, the window will always be pinged to the screen, and then I go back to the other folder. You'll see this way you can quickly compare the result. Okay, so for the subgroup control chart, there's only one data point is out of control, but for the same data, when we try the time-weighted charts in multiple data points, so it has this accumulative effect that it's a way out of control in this case. Okay, if you just unpin the window, then it will go back to the original folder. Okay, just so you know that you can do that. Okay, so after we study the process, we can use this process overview tool to obtain more information. Okay, so here I have the data set. Instead of a one single group column, we have each group data in one row. So at the time 8:30, we have like 8 measurements and etc. Okay, so let's just do a process overview on this data set. So we go to the process overview, and let's say assume the data is normally distributed, and let's start with the normal process overview. Okay, so here for the measure data, I will just use the hunt button to choose from the worksheet, just highlight all the columns. And for the subgroup size, yeah, because this time the subgroup is arranged in rows. So I will just check this box. And we will specify the upper lower limit and the target of the specification. Okay, let's just put the values. Upper value we want to see if this process is satisfy this requirement. In some other settings, yeah, we have seen that those before. Okay, I can still just check all the tests, okay, and click OK. Okay, so this is a report table that's generated. First of all, we can still look at the control chart. So the X bar chart and the R chart, the one data point is out of control, okay? And we can also quickly check the individual data points as a function of time. And from the histogram and the distribution plot, we can tell that some of the data points are beyond the limitation. Okay, so which indicates the process is not within agree with the specification very well. And we can just quickly read the two tables within and the overall. So for the within table, we can tell that the CP value, CPK value are way below 1. So we know that the CP value is the ratio of the specification spread over the 6 times the standard deviation of the data. So the higher the value is, the more capable the process is. So these two values indicates the process itself is not very capable, and there's a room for improvement. Okay, and again, the same for the overall. So here we will use the overall standard deviation for the calculation. And again, the PP and the PPK values are way below 1. Okay, so the overall process is also not very capable. Okay, and other information we can draw from the report is like if you just look at the normal probability plot, the data doesn't follow the normal distribution very well because the p-value is below 0.05. Okay, and we can quickly check the spread or the deviation of the data for the within and overall and for the specification. So you can see the variation of the overall process and the within is larger than the specification. Okay, which indicates the process is not capable. We can sort of like improve this analysis by considering the between group deviation. Okay, so if I go back to the process overview and say I want to check the between and within variation in the process. Okay. Okay, the data is also already selected, and check this box, and again just type in the specification limit. Oh, sorry. 232 and 205. Okay, and yeah, so yeah, the rest of the setting are all the same. So it's this time you will see the individual value or the mean value of each subgroup are within control, but there are other criterion that's not satisfied in the moving average, and also yeah, just one thing to check is the process, the capability of the process. So when considering both the within and between variation of the data, we can tell now that the PPK and the CPK values are very close, which indicates there is between group deviation variation. Okay, and by just looking at the histogram, you will see the overall and the between within distribution curve are almost overlapping. Okay, but but still the process itself is not very capable, as the the the, the index are way below 1. Okay. Okay, so this is the process overview. Okay, let's go to the next capability analysis. So once you know that the process is within control and you're pretty sure about that, then we can do a more precise capability analysis. Okay, otherwise it's not very reliable if the process is not under control. Okay, so in Origin, we go to the capability analysis tab. So again, you will answer the question like whether the data is continuous data. Yeah, so I will say yes. And if whether data is normally distributed, I will say yes. And again, I will start with the normal capability analysis. Yeah, just assuming there is a no between group variation for the data. Okay, so in this case, for the data, I will choose column A. For the subgroup size, I will specify a constant. So I assume the subgroup size is 5. Okay, so every 5 data points are within the same group. And okay, I need to specify the lower and the upper specification limit. And 5, okay. Yeah, other settings like whether you need to transform data, primary knowledge, and here is where how the standard deviation is calculated. Okay, things like that. Yeah, there's some performance display. Yeah, we'll just leave it as it is and click OK. Yeah, it will generate this nice table. And again, in the middle, we have this distribution of the data. Good thing is in this case, all the data points are within the specification limit. Okay, and which indicates it is a good capable process, and you can read the index from the table on the left, and most of these indices are above 1.33, which indicates a good process. Okay. Again, you can compare the CP value and the PP value. They are differ quite a lot, which indicates there's some like between group variation we need to consider. Okay. On the right-hand side, this is the descriptive statistics of the data. And in the lower, there's a performance table. It shows the ppm value. So there's only less than one part that failed. Is below the lower limit for 1 million parts. So which is very low. Is good. Okay. So to consider the between group variation, we need to use another capability analysis tool, the between within capability analysis. Okay. Here, just to quickly show you that I just use the same data. Group size is set to 5, and I need to enter the limit. Yeah, we want to see whether the data is the target is at 5 and the upper and the lower specifications, these two values. Okay. Again, yeah, I'll just click OK. Yeah, so if we include the between group variation, we will see the CP value is more close to the PP value. So more variation gets explained, and you can read other values from the table. Okay. Okay, so this is for the SPC app. I will talk a little about the design of experiment in the rest of the time. Okay. Okay, so an overview of this tool. So DOE is approach helps to understand the factors that will influence a system. It will cover. It will involve couple of stages like design of the experiment and analyze the design, and also you can use the created model to optimize the factors. Okay, so in Origin, the DOE also comes with the app. This app is developed multiple versions ago, but in the Origin 2024, we make some improvement. Just in order to use this app, you need to install the R package first, and then you just go install this app in Origin. Okay. Again, so to view the help documentation of the app, you simply right-click, and you can go to the tutorial web page. It also gives examples and detailed explanations of the app. And also the app has some sample data. You can go to the sample folder to use the data for the tutorial. Okay. Let's just check some of the. Okay. Let's start the power and the sample size calculation. So if I just click this app, there are 4 tools here. Yeah, so first one, maybe the step 0 is to identify the sample size in order to reach a certain power of the experiment. The rest 3 is the design the table and analyze the design and optimize the response. Okay, so let's first check this power and the sample size tool. So in this tool, we support 3 designs, 2-level factorial designs. So each level each factor can only have 2 levels, and Plackett-Berman design. So it's just a simplified 2-level factorial design, but it doesn't allow interaction terms in the design, and the general for factorial. So you can have more than 2 levels, and this is a very expensive design. Okay, so let's just say I want to use a 2-level factorial design, and here you specify the number of factors. Okay, yeah, just assume I have 3 factors, and whether you want to do a full factorial design or a half fraction design. Okay, I will do a full fractional design, and whether you have some factors that you are not interested in, and you want to ignore those factors. So whether you want to include blocks in the design. Let's say I will just set the blocks to 2, and just leave the others as it is, and go to the settings. Here you can choose which parameter to calculate. So you can calculate the power based on the other settings, or you calculate maybe the effects based on the other settings. Okay, so let's just calculate the power. And do you want to replicate for each combination of the factors? Yeah, more replicates means more rounds of experiment and more expensive. And so how much of the effects you want to achieve. So it's the effects here means the minimum difference between the responses for the low end, between the low and the high level of each factor. Okay, so here we want to calculate the power. So this is the grayed out, and you can specify a number of center points, or say 0, and you can give an assumption of the standard deviation of the data. Okay. The settings are just the significance level. And just to mention that you can save all the settings into a XML file in Origin. Okay, so if you just click save and say my setting and save, the next time you can just load the settings. Okay, and just choose my settings to load. Okay. Yeah, let me click OK to run the analysis. Okay, so it gives you the result like if you replicate, replicate twice, and you can reach a power of 0.92, and it also lists other settings of the experiment. Okay, so this is the power and the sample size. Yeah, let's quickly go through one example of the experiment design. Okay, let's choose a signal tool here. There are 2 designs that you can choose from. So the factorial design is more simple. Like once you are able to select the important factors of the design, then you can go to a more advanced design. So where the second order of each factor will be included, then you can use the response surface design. So start with the factorial design. Okay, here is some questions that you can choose a factorial type that I explained about before, and you can click this button to check the design table, and if you know the runs of the experiment and the number of factors, you can get the resolution of this design. Okay, let's just go through an example. So first of all, you specify number of factors. Let's say I have 3 factors, and you can specify a factor name. So let's say it's a temperature, and I want the lower value to be 50, high value to be 80, and I specify another numerical variable, say, okay, so let's give it a name density, and the lower value to be 20, high value to be 30. And the third factor, I will just use text, so a categorical variable. Let's say type. I can say type, give it names to type A and type B. Okay, and then we go to the settings. Okay, you can choose a full factorial design or fractional half fraction design. Okay, I will do a full fractional design here. Okay, and yeah, I want two blocks, and I want each experiment, each combination of factors will be repeated once. Okay. Then there are other settings. Okay. How do you want to randomize the each rows in the table? Okay, just leave other settings as it is, and I click OK. It will generate this design table. Then you can just go ahead and do the experiment. So you can just add a response column and fill in with the measurements, and then you can do the analysis. Okay, so assume that, let's see, okay, assume I already have this table that experiment has been done. Okay, so the column D is the response. Then I can analyze this experiment. So I would say analyze design. Okay, so here again, let's say the response, I know it's the column G, which is the response, it's the pH value, and so how the order of the model. So I want to include the interaction, so I choose the second. Okay, so you can also customize the model by manually add. If I say order 2, that will add the second order interaction term. If you choose 3, then all 3 factors can be interacted. Okay, yeah, I'll just go back and choose the order 2 here. And yeah, since in the design we have included the blocks, so I include the blocks in the model, and the confidence level and the quantities. Okay, for the coefficients table, you can include the t-value in the, yeah, if you want, you can include the p-value as well. Okay, there are other things. Okay, yeah, you can also do a prediction. Once the model is generated, you can find the y from the x. Okay, then for the plots, I will also, yeah, let's just include all the plots here. Cube plots, contour, surface. Okay, so for the cube plot, you will need to include all 3 factors here. Okay, and for the let's see, for the contour and the surface plot, we will specify the x and y. They both have to be the continuous factor, and for you need to specify the value for the categorical factor. Let's say I want to just check type A in this case. Okay, let's click OK to view the result. Okay, so yeah, you can just view the coefficients for each factor and also the interaction term. For the ANOVA table, you can tell which factor is more significant. Let's say the block, yeah, the p-value is very small, so it's significant, and the temperature density is not that significant. Okay, also the categorical variable reagent is significant. Okay, and you can quickly check the effects table, and yeah, you know that reagent is the most important factor here. Okay. Yeah, main effects plot. Okay, you can check the two-way interaction plot. If all the lines here are parallel with each other, which indicates there's no interaction. Okay. So for the cube plot, you can quickly tell the response at the combination of the three factors. Okay. So yeah, for example, like if for the temperature at 80 and the density at 20 and the type A, we get a response of 6.275. Okay. Yeah, other plots also just confirm the conclusion. For example, if you go to check the surface plot, we can tell that the response changes a lot along the temperature direction, but doesn't change much along the density direction. Okay. Okay. Then we can use this generate model to do optimization. Okay, I just quickly show you optimize response. Okay, so here I assume you just choose a goal for the optimization. You can say I wanted to minimize the response. Okay, and you need to specify a lower and upper limit. Okay, so yeah, if you quickly check the cube plot here, the lowest value may be I may not go below 0.6 and the upper limit may not go up above 9, let's say. And for the setting, you can apply some constraints for the factor values. Yeah, just leave it as as it is. Yeah, just make sure I will check the optimization plot. Okay, and then click OK. Okay, it's running in the background. Okay, let me close this. Okay, so it gives us the solution that at the temperature of 80 and the density at 20 and the reagent is type A, we get the minimum response pH value, which is 6.275. Yeah, it's which is agree with the cube plot here, right? Okay. One thing is you can, if you double click on the optimization plot, it will initialize the plot based on the optimized values of the factors. You can just drag the line to view the response at different combination of the factor values. Okay. Yeah, if you click reset, it'll go back to the optimal position. Okay. Yeah, so now this is for, yeah, there's some time. I just quickly show you the sample component. Yeah, I'm not going to show the procedures, but just so you know that you can use the DOE to analyze the model of more than one response. So here I have two responses. Okay, you can use the model to use the tool to analyze such kind of data. And in the report, yeah, as I said, this more advanced model design model allows the second order of the factors. So when you check the yeah, let's just check the surface plot. yeah, you will see the the surface is no longer a plane now. It's like a curved plane. Okay, and again, you can tell the response is increased by time and also increased by temperature in this case. Yeah, just some quick conclusion. And also, if you use this model to do optimization, you should be able to get, you can optimize the two responses separately. Say, I want to maximize the pH value, but minimize the conductivity. And you can set the goals, these goals simultaneously. And for the optimization plot, in this case, you will see, yeah, the curve are no longer like a straight line. It's more like curved, okay, because we are using a more complicated model in this case. Okay. Yeah, I think that's all for today's webinar. And if you have any questions, just feel free to send us a ticket. And we strongly recommend you to test these two apps that we either newly developed or have improved quite a lot. Okay, thank you again for your time and for your patience. Have a great day.